Welcome back to the deep dive. If you've ever interacted with a smart AI chatbot, maybe for customer service, memory is everything. If it forgets what you were talking about even a few minutes ago, the whole conversation breaks down. Today, we're diving into a challenge for anyone building serious AI systems. How do you handle hundreds, maybe even thousands of messages in a chat without the AI losing the plot? Some really interesting work from IXO point to this elegant solution called rolling window summarization with context injection. And that's our mission today, to really get under the hood of this technique and figure out how it gives AI essentially perfect long-term recall.
Yeah, and that memory challenge, it's fundamental. It comes out of a really basic technical thing. Token limits. For anyone maybe not deep in the weeds, the large language model, the LLM, can only look at so much text at one time. That text gets chopped up into tiny bits called tokens. If your chat history gets longer than that token limit allows, the AI basically goes blind at the beginning of the conversation, just can't see it anymore. When you're trying to build persistent memory, the old ways are pretty terrible. You either try summarizing everything, but then you hit those token limits super fast and lose all the subtle details, or you process each message one by one, but then you lose the flow, the context. What we really need is efficiency and perfect history. That's the goal.
Okay, let's unpack the core idea then. It sounds quite clever because it sort of mirrors how we manage complex stuff, right? Use this analogy. Think of reading a really long book, like a huge history text. You can't read it all in one sitting. But when you start chapter 2, you need to remember exactly what happened in chapter 1.
Exactly. And that leads directly to the first step, window creation. Instead of shoving, let's say, 50 raw messages into the LLM all at once, which it probably can't handle anyway, you split those messages into smaller, digestible windows. The default is typically 10 messages per window. So those 50 messages become window 1 with messages 1 to 10, window 2 is 11 to 20, window 3 is 21 to 30, and so on.
Right. So immediately you've chopped the complexity down, made it manageable for the LLM at each step. But here's the thing that jumps out at me. If you're summarizing these little 10-message chunks, aren't you just creating a bunch of separate summaries, little islands of information? What stops the system from basically forgetting everything that happened in window 1 when it moves on to window 2? How do you bridge that gap?
That is the critical question. Because if you just did simple chunking and summarizing, you'd have exactly that problem memory loss between chunks. This is where the real magic, the secret sauce, comes in, context injection. This is what turns isolated chunks into a connected memory chain.
Okay, this is where it gets really interesting, I think. How does it remember the summary from window 1 when it starts working on window 2?
It's quite clever, actually. It doesn't rely on some external database lookup between steps. It uses the LLM itself to maintain the context chain. So when the system gets ready to process the next window, let's stick with window 2, so messages 11 through 20, it doesn't just feed those 10 messages in isolation. It prepends, meaning it puts at the beginning the summary that was generated from the previous window, from window 1. So if you look at the actual structure of what goes into the LLM for that second step, it's basically summary of window 1, which might be, say, 4 dense messages, plus the actual raw messages, 11, 20, the 10 new messages. The LLM then takes that combined input and summarizes that to create the new summary of window 2.
Ah, I see. So those few summary messages from the first block are pasted into the instructions for the second block. They act like the AI's working memory for that step. That guarantees the context flows through from the start to the end.
Exactly. That's how you get this continuous context chain. The summary of window 1 informs the summary of window 2, which informs window 3, and so on.
Oof.
By doing this, basically 100% context retention between these windows. Doesn't matter how long the conversation gets.
Okay, so the system knows how to break it down the windows and how to link them, the context injection. But now let's talk about the summary itself. What's actually in that summary? What are the LLMs told to focus on when they do this compression? It can't just be a vague recap, surely. Oh, absolutely not. Generic summaries would be useless here. The instructions, the prompt given to the LLM for this summarization task are very, very specific and strict. This is really the heart of making it work. It's not just about making the text shorter. It's about preserving specific kinds of information and structuring it correctly for what comes next. Yes, there's information preservation, capturing key facts, any decisions made, answers given. But critically, there's a huge emphasis on entity extraction. Non-negotiable. Specific names of people, places, project names, numbers, dates, technical terms, all those must be kept perfectly intact. No fuzziness allowed. The system is squishing the surrounding text, but it needs to keep every single proper noun, every key data point absolutely clean.
And why is that so rigid? Why the intense focus on keeping those specific entities like Alice or Project Chimera perfectly clean, even in a summary? Because the end goal here isn't just a human-readable summary. It's preparing data for something else. If you compress "Alice met with Bob on Tuesday about Project Chimera" into something generic like "two colleagues met about the project," you've just destroyed the crucial data points. You need Alice, Bob, Tuesday, and Project Chimera to survive. The process also demands preserving role attribution, who said what, and temporal flow, keeping the sequence of events logical.
Okay, the structure matters as much as the content. Which leads us to the output format. The LLM doesn't just spit back a paragraph of text.
Correct. It returns structured data, specifically JSON, that perfectly matches the schema for messages.
This is really key for anyone listening to grasp. The summary messages aren't just text blobs. They're treated like new, super condensed messages that fit right back into the system. So the output would capture like the dense summary content itself, but also the specific role like Alice or AI assistant, and even the correct timestamp. It's compression without losing the structured information. It's database ready.
Precisely. Database ready is a great way to put it. And that structure is absolutely vital because, connecting this to the bigger picture now, this whole sophisticated summarization process, it's totally necessary for the system's ultimate purpose, which is often building these powerful memory graphs. Think of a memory graph as a way to turn all that messy back and forth conversation into a clean, structured knowledge base. It's like a map of the conversation, with facts and entities as the points and the relationships as the lines connecting them. And you can only build that kind of structured graph reliably if the input data is already clean, structured, and entity-rich, which is exactly what this rolling summary provides.
So instead of the memory graph system trying to wade through, say, 50 raw messy messages, it only has to process maybe 20 highly refined, pre-digested summary messages. What does that actually do for the AI's performance? Speed. Capability.
It provides 4 key benefits. These allow the whole thing to scale up. First, it preserves entity information. Those clean names, project titles, dates, they become perfect nodes for your graph. No ambiguity. Second, it maintains relationships. Because you've kept track of who said what attribution, connections like Alice works with Bob on Project X survive the compression. That becomes an edge in your graph. Third, and this is huge, it massively reduces processing load. Fewer messages to analyze means the graph can be built much faster. Less compute costs, too. And finally, it enables scale. You can now handle conversation histories that are way longer than any single LLM could process in one go. It unlocks handling truly massive amounts of text.
That volume reduction seems really striking, turning 50 messages into just 20 summary messages. That's a 60% cut in the volume the next system has to process, while crucially keeping apparently 100% of the important context needed for that graph. That's incredibly efficient.
It really is. Efficiency squared.
We've got the core mechanism, the rolling windows, the context injection, the summaries. But the system seems to have some extra layers of cleverness, too, these smart features, things that make it more than just a basic summarization loop. Does adding all this extra logic, though, ever slow things down or make it harder to manage?
That's a very fair point. Complexity can definitely add overhead. But ways to manage that, primarily through adaptive intelligence. One fascinating bit is how the system actually changes its instructions based on where it is in the conversation chain. Adaptive prompting.
Adaptive prompting, how does that work?
Think about it. When it's processing an intermediate window, say window 3, summarizing messages, the prompt it gives, the LLM basically says, summarize this, but make sure you preserve context for the next window. It's preparing for window 4. When the system reaches the very last window of the entire conversation, it knows there is no next window. So the prompt changes. It tells the LLM something like, this is the final summary. Make sure it contains complete standalone context.
So the very last summary generated is useful immediately on its own. It doesn't leave you hanging, waiting for a next step.
Exactly right. Ensures the final memory record is complete and actionable. Then there's also flexibility through configurable thresholds. This is more on the practical side for developers using it. You can tune things like the window size, maybe 10 messages as default, but you'd make it 8 or 15. You can control the summary size. Maybe you want 4 summary messages out, or perhaps 3 or 5. Importantly, you can set a minimum number of messages required before summarization even kicks in. Say a threshold of 10 messages. If you have a really short chat, maybe just 5 or 6 messages total, this saves processing power for trivial conversations.
No point summarizing something that's already short. And what about the different people talking, since tracking who said what is vital for the memory graph?
It has to handle that. Multi-speaker awareness. It's designed to automatically figure out the conversation pattern. Is it just one person dictating notes? Or is it a more typical back and forth between a user and an AI assistant? It adapts to ensure that those distinct speaker perspectives, user said X, assistant said Y, are clearly preserved in the summaries. which is critical for accurately building those relationship edges in the graph later on.
Okay, last piece then, maybe the most practical one. Resilience. What happens if one link breaks? An API call to the LLM fails for one window, or the LLM returns garbage for some reason. Does that just completely destroy the memory chain from that point forward?
That's a crucial failure point to consider, definitely. And built-in graceful degradation. There's a fallback. The ultimate safety net is this. If, for whatever reason, the summarization for a specific window fails, maybe the LLM times out or gives a bad response, the system is designed not to use that failed summary. It won't inject garbage into the next step and break the chain. Instead, it falls back to using the original raw messages just for that failed window when it processes the next window. Oh, okay. So if summarizing window 3 fails, when it goes to process window 4, it will prepend the original messages from window 3 plus the summary from window 2. Exactly. It means a single failure only impacts the efficiency of that one small segment. You lose the compression benefit for those 10 messages, but the context integrity for the entire rest of the conversation remains perfectly sound. The history isn't corrupted.
That failure doesn't cascade and ruin everything.
It's window-level resilience. The big takeaway for you listening is building really good AI memory, the kind that can handle long, complex interactions. It's not just about having a big database to dump text into. It's about intelligent compression, smart, multi-layered processing that preserves vital information, the structure, the entities, the relationships, and this rolling window approach with the context injection and strict summarization rules seems like a really elegant way to achieve that. It turns this massive, messy text stream into chained, dense, structured data ready to power advanced applications like memory graphs.
Yeah, it allows for AI that doesn't just store words, but actually understands and remembers the flow of conversation no matter how long it gets. And it does it efficiently without huge delays or crazy costs. Thinking ahead, the listener may be wondering where this field is going next. Some interesting future upgrades beyond what we've discussed, things building on this foundation.
Thinking past fixed parameters. Imagine dynamic window sizing. Instead of always using 10 messages per window, the system could adjust that number on the fly. If the conversation gets dense with important info, the window shrinks to capture it more granularly. If it's just chit-chat, the window gets bigger.
That makes sense. Adapt the chunk size to the information density. Semantic chunking.
That's moving beyond just counting messages. Instead, you'd group messages based on their topic or meaning. So if you have 4 messages scattered across a window, but they're all about Project Chimera details, the system could group those together into a semantic unit for summarization, even if they weren't consecutive, more intelligent grouping. The really obvious next step is multimodal support. Conversations increasingly involve images, sometimes video clips, code snippets being shared. How do you integrate those into these dense, structured summaries? That's a big challenge, but clearly where things need to head for truly comprehensive memory, always pushing for richer context.
Hopefully, understanding this rolling window technique gives you a much clearer picture of how sophisticated AI systems are being built to actually remember and learn from our interactions at scale. Thanks for diving deep with us today.